Hi, Benny. Hi, everyone. We'll wait a few minutes to see whether the numbers go up.
Hello. Sure.
And by the way, Benny, thanks for taking the time and joining us today.
Absolutely. Pleasure.
Okay, we are 5 minutes in. Maybe today we're gonna have lower attendance than usual, but well, too bad. Um, anyway, Benny's here to talk to us about Intel's PoE, which is an endorsement that can be used to associate ownership information to attesters, I think. And Benny was scheduled to talk a month or so ago, 2 or 3 calls back, if I remember correctly, because we wanted to have him and Milos back to back. But because both Milos and Benny are looking at quite similar problems, which also overlap with the Nasr problem and the general problem of associating location/ownership attributes to hardware that is involved in some confidential/trusted computation, be it network path computation, workload residency, and so on and so forth. But yeah, I hope you still have Milos talk in fresh in your memory. But if not, there should be a recording of that on YouTube. But yeah, I would leave now, Benny. You have the floor. So take the ownership of the whole thing and let me know how you want to take questions, whether you want to take questions as you go or at the end, etc. Whatever.
First, you see my slides now, is that correct?
Yes, I see that very well.
Perfect. Then, yeah, thank you very much for having me. Everyone that's here, everyone that potentially will watch the recording later. I'm Benny Furi, working at Intel. I'm in what we call our confidential computing enabling team, right? So I'm the guy that mostly talks to customers, partners, internal teams to help them use confidential computing with whatever it takes. And yeah, today I have the pleasure to talk to you about platform ownership endorsements. This topic was also presented at the CCC TAC a few weeks ago, right? So if you watched or regularly watch the tags, then this might not be really new for you. If you didn't watch it, then most certainly this is new. Feel free to the question that was just asked, feel free to ask questions at any time, right? I will try to watch my screen and see shown of hands and so on. So feel free to to ask questions at any time. With that, today we will talk about what we call platform ownership endorsements, or Intel, or PoE for short, which is a mechanism to strengthen the trust in the confidential computing environment. or like very high level introduction. You know, technologies like Intel SGX, Intel TDX, and also competition, right? We do an excellent job in protecting the workloads from software-based attacks. Yeah, but there's unfortunately a gap when it comes to physical attacks, which I will later briefly discuss. But the issue is, even if a customer assumes that there are no physical attacks, there still needs to be a possibility to verify who physically owns and controls the hardware, so that you can be sure, okay, I trust party A, but I must know, okay, party A is the one that owns my hardware, right? And this is what PoE is mainly about, and you will hear that over and over again in the presentation. And I will walk you through the threat model of the physical attacks create. I will review remote attestation at a detailed level as it works today. I will show how physical attacks can compromise this remote attestation flow, and then I will introduce in detail the PoE solution and how we, with it, tie attestation evidence to trusted physical owners. And yeah, with that, let's go into it, right? First, we call it here like the physical attacks are in the elephant in the room for confidential computing, right? Because as already said, SGX and TDX, they protect your workloads from software threats, but basically from day one, when confidential computing was introduced in server CPUs, Intel considered physical attacks out of scope, right? Like that's what we legally say, it's out of scope. It doesn't mean we don't care, right? Please don't mix them up, but legally it's out of scope. And in practice, an attacker with physical attacks to a server can carry out certain types of attacks, and basically like not new these are known attacks, but compared to just a software attacker, a physical attacker can do other things. For example, he can do memory probing and bus observation, which means that you like to physically tap into the data line between the CPU and the main memory to read what's being transferred. Second here, he can deliberately cause hardware errors to manipulate calculations or leak secrets by fault injections, for example. Then there are so-called cold boot attacks, like freezing down the main memory and with it, the content, putting it in another machine and reading it out, right? I guess most of you have heard that before. And in particular, an attacker can watch encrypted data patterns and manipulate the ciphertext to cause predictable changes in the plaintext. And last year, especially about the last one, last year we saw critical attacks or researchers that used this attack vector to leak some data, and we will look into what they exactly leaked. We'll look into this later. But importantly, in this talk, we assume a type of a customer which trusts their cloud service provider, or if it's not a cloud service provider, any infrastructure provider, right? The customer has to trust the infrastructure provider to not do such attacks, right? That's the point. And in this case, when the customer trusts that the infrastructure provider doesn't physically attack its virtual machines, its confidential virtual machines, the main goal is to verify who actually physically owns and controls this platform running the customer workload. In theory, almost every information needed to achieve this goal is already present in attestation structures today. We will see details later of that. So far, nobody used them, unfortunately, and I guess we are to blame here a bit as well, because no hardware vendor ever explained how the structures that are already there can be used to gain trust in the physical ownership of a platform. Yes, and this is precisely what platform ownership endorsement, the architecture, is about. We want to create a verifiable cryptographic link between attestation evidence and the trusted physical owner of the hardware. Intel published a white paper of this presentation basically at the end of last year, with the main goal of the industry ideally would move to multi-hardware, multi-vendor, and multi-infrastructure provider solution, right? Because as said, like all the structures, like all the information is already there. But if now everyone goes ahead and creates its own version of that architecture, then it will be a mess, right? So that's why our first priority, even before putting out a line of code, our first priority was putting out the architecture as a white paper, so that the industry can at least see and ideally give us feedback of how we want to do that. Just to really enforce that, platform ownership endorsement is not about protecting against physical attacks. It's not. It is about the putting trust in the platform ownership. At OC3 this year, Simon Johnson from Intel gave a presentation about potential protecting mechanisms against physical attacks, but in this presentation, it's completely out of scope. So I don't see any questions, so let's go on. And before moving into the details of the attacks, platform ownership endorsement, let's make sure that everybody understands how remote attestation works in the Intel TDX architecture, right? As this is the attestation working group, I guess most of you know by heart, potentially even, but maybe I saw a lot of people from AMD and ARM, you might not be that familiar with Intel's process, right? So let's go into detail of how it's done in our case. During the setup phase, like you buy an Intel CPU, a platform with Intel CPUs in it, and the first thing you have to do with an Intel CPU is you have to do a setup. And the setup starts with a platform registration. Like on initial boot of this platform, the CPUs talk to each other. They will generate what we call a platform manifest. And this platform manifest is sent to an Intel service. Intel service recognizes the Intel CPUs that are listed in the platform, checks that they are valid Intel CPUs, and creates an appropriate, what we call provisioning certification key certificate. Very long name, right? I will abbreviate this PCK certificate for most of the future. So in this PCK certificate, like I said, platform manifest reaches the service, it checks it, generates this PCK certificate, and provides it back. Then also, we are still in the setup phase. This might happen really on boot, or this might happen when the first quote comes in. It's not really important. But at some point, the following happens. A so-called TD quoting enclave comes up. It's an Intel SGX protected enclave, which generates an attestation key, which is an asymmetric key pair. The public part of this attestation key is provided to what we call a provisioning certification enclave. So again, an Intel SGX protected application. This provisioning certification enclave checks that it speaks to a valid TD quoting enclave by comparing its hash, and it checks that they run on the same machine. When both checks are a success, the provisioning certification enclaves generates an attestation key certificate. Right? We see that on the right now, which it signs with the PCK. So looking back at what we have now, Intel provided a PCK certificate. But the only instance on a machine that's able to access the PCK, so the secret key especially, the secret key of it, the PCK secret key part, so to say, is this provisioning certification enclave. So again, public part of attestation key comes in, provisioning certification enclave checks it, and signs it with the private key. And then we have now we have two certificates you see on the right side, right? The PCK certificate and attestation key, which is signed by the PCK certificate. Good. Then the attestation phase starts. The relying party comes in, requests evidence from the trust domain. Trust domain goes to the TDX module. TDX module goes down to the CPU hardware. And the CPU hardware generates what we call a TD report. This TD report contains sensitive information about the DD, the TDX module, and the hardware itself. And this TD report is protected, integrity protected with a hardware-bound MAC. That's what we now see here on the top. This TD report is returned back to the TD, back to the hypervisor, back to the TD quoting enclave. The TD quoting enclave uses this MAC to verify that the TD report was generated on the same platform. On success, it signs this report with its attestation key, right, that it generated before. It generates it, it signs it with the attestation key, which is then what we call a TD quote. This TD quote is forwarded to the hypervisor, to TD, to the relying party, which does quote verification. For quote verification, the relying party has to reach out to Intel to get our verification collateral. For example, what is the newest TCB level, what certificates were revoked, and a lot of other, not a lot, but a few other pieces of information. And then it checks the quote. The key takeaway from this slide, the entire trust depends on the integrity of the keys and the certificates. This is by far the most complicated slide I have, right? So feel free to ask any questions. Nothing? Good. Then let's go on. Now let's look at a concrete example of physical attacks on Intel SGX and TDX. And the approach that I show here involves physically deploying a DRAM bus interposer, which is a device placed between the CPU and the main memory modules. And you see that in the picture, right? It's really your main memory and your interposer. I'm pretty sure most of you saw these pictures before. These images show this physical setup that are used by researchers for the attack I'm talking about now. Critical detail here that is basically used, critical detail about the technology, about Intel SGX and TDX, and to my understanding, to competition technology, we use deterministic AES XTS encryption. In our case, this means in more detail, deterministic here means that the same plaintext data is encrypted, like the same plaintext data encrypted to the same cache line will produce the same ciphertext, right? So it's not. So we use a little tweak that is cache line dependent, but nevertheless, on a higher level, the same plaintext will end up the same ciphertext. And unfortunately, by exploiting this deterministic behavior and reading it really directly from the main memory, right? It was not a software attack, because with Intel SGX and TDX, when a software tries to access these memory locations, we return 0, right? To not give the opportunity to do any ciphertext analytics and stuff. But these attackers, they put a main memory interposer in between, and then they were able to see the data that is written to the main memory and read from the main memory. It's encrypted, right? But they were able to read it. And unfortunately, they were able to leak the provisioning certification key, right? That's why I went into so much detail on the slide before. They were able to leak this private part of the provisioning certification key. And this key is crucial for the chain, as we saw in the diagram, and compromising it effectively breaks the trust in remote attestation. So that's obviously an issue. So first, let's see what are the consequences when an attacker has access to an attestation key. With the compromised key, attackers can generate TD quotes containing completely arbitrary content. You see on the right side what they broke, right? They leaked, they were able to get the private key that can be used to sign this certificate, and by having access to that, they can generate arbitrary quotes. And let's look at some concrete attack vectors here. They can, for example, define arbitrary report data. Report data in a TD quote is it's user defined, so it can be used for whatever. But in a lot of use cases, it's, for example, used for nonces or for a hash of a public key or stuff like that. And which could mean if an attacker is able to change report data now, because they have broken the PCK key, they can change the nonce, right, and break freshness with that, or they can put in their own public key, which would be catastrophic, basically. They could also define arbitrary TD attributes, and TD attributes, as there are multiple of them, but for example, there's one defining if it's a debug trust domain. So what could an attacker do? He could set up a debug trust domain, like a trust domain is our term for confidential virtual machine, right, or Intel TDX protected virtual machine. They can bring up such a TD and pretend it is in production mode, or pretend it's not in debug mode when it actually is, because they can lie in the quote. They can also define arbitrary MRTD measure values, and MRTD is the hash of the virtual firmware that's used in the TD. So again, an attacker could claim genuine firmware is running when actually some malicious firmware is running. So important and, in my opinion, dangerous part is that the relying party would accept these forged quotes as completely legitimate, because the certificate chain still traces back to Intel, right? Everything is good here, and the customer has no idea that this is faked and this is faked. So the forgery is actually indistinguishable from a genuine quote. There's only one thing Intel can do, and which we did for these researchers, for example. Once such a compromised attestation key is identified, Intel can revoke the platform and even each individual CPU in the platform. Right? So we have a certification revocation list exactly for this purpose. However, there's a critical window of exposure between the time the key is compromised and the time the key is revoked. In that time, there's no way to recognize it's a faked key. And this is exactly why we need PoE, to add an additional trust mechanism beyond the certificate chain alone. Any question? Please don't be shy. Yes, please.
So Benny, when you say attestation key is identified as compromised, but how practically that can happen is not clear to me. Because it can stay forever, right, as a compromised key without necessarily anyone noticing that, isn't it?
What is the question? How could we revoke it? Is your question?
No. The mechanics of revocation is clear, is a mechanical process. How you identify the fact that that specific attestation key has been compromised? That's the thing, right?
Yeah, good question. And in most cases, we can't, right? If an attacker doesn't behave in any invalid way or any obvious way, we can't.
Right. Okay.
That's a fact. So if you break your own server in your basement, you pretend all is good here and you use it forever and don't do anything spoofy, we can't. But in this case of these researchers, right, they created the Twitter bot to generate quotes. Right? In this case, it was pretty easy for us because we just have to look at the quote and then can basically revoke the platform.
Oh, okay, so observing quotes from the malicious platform, then you can.
Yes.
But then the problem is how do you know that these are malicious? So effectively, this window can become infinite, right? Once
exactly. This is a problem. It's 100% a problem, right?
Okay.
And this is, I guess, like why we like the next thing, right? Hardening remote attestation. But the thing is, I mentioned it before. The important thing is we want to have a solution that protects you if you assume the owner of the infrastructure does not attack you. That's the point, right? That's all we want to solve here, right? We don't solve physical attacks. We don't solve recognizing that a physical attack happened. That's not what we do. What we do is, customer, if you have an infrastructure provider for which you trust that he doesn't physically attack you, then here's a solution for you. Yeah. And importantly, like it's important to understand, like just one random example, right? Or, a customer uses Azure and says, I trust Azure, or it doesn't matter. It's Azure, Google, AWS, whatever, name your infrastructure provider, right? Many customers come to us and say, hey, I trust that these guys do not physically attack me. Because especially those guys, they put up fences, guards, doors, lockers, whatever, cameras. So they will not physically attack me. But importantly, at the moment, nobody knows how to recognize even that you talk, like you go to one of these hyperscalers, get an Intel TDX protected virtual machine, but how do you know that it runs there, right, at these hyperscaler? And it's not some attacker that has broken his machine in his basement or in his garage and then says, hey, I'm the hyperscaler, please come to me. That's what we want to solve, right? Differentiate between legitimate platform owners that you trust and ones that you don't trust.
Cool. Thank you.
Sure. So given that these physical attacks break the trust assumption of remote attestation, right? That's what we talked about. How do we harden the attestation process? And that's exactly what I just mentioned, right? From a reliant party perspective, two things must be possible. They must be able to recognize the physical owner of the machine. They must know, I trust infrastructure provider A, and this machine is a physical infrastructure provider A, and not by even another trusted infrastructure provider B or an attacker, right? That's what they have to be sure about. And they must trust that this physical owner does its best to prevent physical attacks, right? Because again, we don't protect against, like it's not about, the solution is not about protecting against physical attacks. And the key insights to do this platform ownership endorsement is first, the attacker cannot modify the PCK certificate, right? So the bottom of this chain cannot be modified by the attacker because the PCK certificate is signed off platform by Intel, and the attacker cannot access Intel's private key just by attacking the machine, right? He could attack as many machines as he wants, still Intel's keys at somewhere completely different location. Sure, you could brute force it, right? But that would completely break any signature scheme we believe in. And second, the PCK certificate contains a unique platform identity. In technical terms, we call it the PEID, the Platform Instance ID. Just to make it a bit easier in the future, in the following of this talk, I will just use Platform Instance ID. I'm not sure. Platform Instance ID or Platform ID, I will just use them interchangeably. This ID, importantly, is generated randomly on first boot. It survives reboots, and it can be reset explicitly by the user by going to the BIOS and doing an Intel SGX factory reset. So it's persistent in normal operations, but still has a defined reset mechanism when required. And this is really important because assume an attacker buys a machine with Intel CPUs, leaks the PCK, gets the PCK out, and gets the ID out. Then he could potentially, and then you just buy this machine from the attacker, you generate your quotes, then they could not be differentiated from each other, right? He could still fake quotes, and they would not be distinguishable from your quotes. But when you receive a machine, if you go to the BIOS, do an Intel SGX factory reset, everything starts from scratch, right? You will have a new identity, a new PCK key. You also need to do a new registration, but like everything is new. And the same when you end of life a machine, right? Before you end of life it, ideally go to the BIOS, do an SGX factory reset, and end of life it afterwards, because then nobody can pretend afterwards that the machine still belongs to you. So in summary, we anchor ownership to something the attacker can't tamper with. We have an Intel signed PCK certificate, which the attacker cannot change, that carries this unique platform ID. Good. And before looking into the actual proposal that we from Intel have, we will first look in a strawman flow of PoE to make it a bit easier to explain the basic principles. Yeah, please, question.
Yeah, what is the benefit of PID surviving reboot versus forcing the owner to go through the bootstrapping of the PoE each time upon reboot? I mean, is there any loss of security by forcing the owner to do that?
No. I guess there are different perspectives here, and Jim, please jump in to correct me, right, if I say anything wrong or miss anything here. Importantly, for things like the keys, like when you do an SGX factory reset, all keys will change, like all keys, right? So, and in the future, for example, if you will be able to seal secrets to a trust domain, then the sealed secrets cannot be longer unsealed when you do an SGX factory reset, right? So you have to be careful you should not do an SGX factory reset just because you have to, right? It doesn't break your security if you do an SGX factory reset each time, but it also doesn't help you. Because importantly, like as you will see on the next slide, you will see that the platform instance ID is used to track your platform over time, right? And sure, you can have a new platform instance ID after each boot, but there's not really a benefit of having a new ID on every boot.
Yeah.
Right? It's important that when you buy an external one, then get a new ID, and ideally before you ship out, then Jim, please.
Yeah, just to continue on that though, CVM sealing keys are not expected to survive a reboot, right? Unless the CVM itself somehow persists it. I mean, whatever's
so in the Intel SGX world, right? We don't have sealing at the moment in TDEX. We had Intel SGX sealing, and there they would survive reboots, right? You could seal data, do reboots as often as you want, and you could unseal it afterwards. They were hardware-bound sealing keys.
Okay, but you don't have that in TDX. All right, thanks.
Yeah, I would say that if the assumption is that PID changes on every reboot, that's not true. So there are values that survive reboot. So here you
Yeah.
have to do
The question
specific.
is why don't they change? Why don't we change it on every reboot? Was the question. I made the statement they do not change. The question was why don't they?
Yeah, that's right. Yeah, please continue. I think I got the answer to my question. Thank you.
Mo, please.
I mean, I could see one benefit for this, honestly, of being changing upon reboots is in the case of for example, when the machine gets dispatched away from the fleet and forget, like the owner forgets to do the factory reset before. So whoever gets their hands on afterwards might conduct any side channel. That's one of the reasons, or in case of stealing, if one of the machines gets stolen from the rack, then technically.
But the entire purpose of sealing is to
No,
survive.
not stealing,
Yeah.
not stealing,
For
stealing.
this idea, yes.
Yeah.
Yes. Yeah. Okay, I guess we can discuss it in the end again if this is important or not. I think it's not. I think it's better. Like, it's a trade-off, right? We could, I guess, in theory, have a thing that will refresh on every reboot, but I guess it's a benefit to not have it on a new one on every reboot. And I think this will be clear on the next after we discuss the flow. So, as said, strawman construction first. Right? It's not what we propose, but just to make the explanation easy. So we're here in a supply chain or maintenance phase, we call it. So when you first buy such a machine or you do some maintenance on the machine, you put up a new firmware or whatever. This is what we talk about here. Then the admin goes to the machine and collects these PEIDs, the platform IDs. On every target platform that should use this PoE architecture. This collected platform IDs I send to a public repository and publish there. Publishing details are implementation specific, right? So the platform owner, he could put it on a website, hey, these are all my ideas, or you can put up a public endpoint that says, hey, ask me here if this is my ID, right? So the only important thing is, like, it's the owner. The owner puts up a list somehow, somewhere, saying these are my platform IDs. And then in the production phase, we have our target platform and an attestation service. As usual, an attestation is requested at some point, and a quote is created. The resulting quote is provided to the attestation service. The attestation service does its usual quote verification, which might include quote appraisal, right? Again, implementation specific. And now the additional new step is the attestation service retrieves this public list of IDs. Again, it depends on how exactly it's done. If it's a website, go to the website or read some endpoint, whatever, right? But go to the platform owner, to its repository, and ask for the ID. And then platform ownership verification happens. And it's pretty easy in this case, right? You look at the quote contains the platform ID, because every TD quote contains the PCK certificate. It's basically attached at the end of every TD quote. There's the PCK certificate. So the verification service looks at the PCK certificate piece of the quote, read the ID, and check if it's an ID that's on this list of an owner. And using this flow, right, just by this, let's say, easy flow, the attestation service made sure that the quote was generated by a platform owned by the expected platform owner. Let's briefly talk about a potential attack that you might have. Like, at least when I talk to most customers or most people for the first time, they're like, but that doesn't make any sense, because what prevents an attacker that has, like, let's say hyperscaler A says, hey, my list is 100, 200, 300. Then an attacker comes there and says, hey, I also have the platform with ID 200. Right? And there's no way to say who is true, like who is correct now and who is lying. But importantly, only one of those two can generate valid quotes. An attacker, if he claims he has an ID with number 200 machine, which ID 200, he will not ever be able to generate a corresponding quote that successfully validates. But the actual owner of the platform can. This is just a strawman's construction because it has two issues. First, the platform IDs are not integrity protected by themselves. Sure, if it's on a website, you can trust the integrity of the website itself, but it's not directly as attached to the IDs. And second, at least that's our assumption, most CSPs will not be willing to publish such a list, right? Because it really leaks how many Intel machines or whatever machines they have in their fleet, which is normally business secrets that they don't like to share with competition. Question to the strawman flow.
Sorry, I was a bit late since I had a conflict. Sorry if the question was already asked. So I just want to check. So for the PIID, how stable is it? Does it change for firmware updates or SGX factory reset?
Mm-hmm. The second, like you asked two different scenarios. For updates, it changes on updates. Every update, like every TCB level relevant update, right? Where we will, in that case, we generate new PCK certificates and new PEIDs. Yes. The other question, half of the question was just discussed on the slide before. It doesn't, PEIDs survive reboots, but they can be explicitly be reset with an SGX factory reset in a BIOS. Giri, please.
Yeah, sorry about that. I didn't understand the comment about, or maybe I need some clarification on it would be changing per TCB update. So that would be even for hitless updates as well?
So what was the last part about what updates?
Hitless updates.
Hitless update, I think it's not a term we use.
I think it means hot loading.
Yeah.
If the patch is applied without a machine reboot.
Yes, exactly.
Jim, maybe.
I think there's a lot of different terms for this, but inside Intel we call it TD preserving. So you could do like an OS loaded microcode patch or an OS loaded TDX module, those kinds of things. Yeah, the PIID does survive those. It can even survive a BIOS update if you can restore what we call key blobs. Key blobs are signed for max structures that are stored in flash.
Okay, so they don't need to change for TD preserving updates then, is what you're saying, even if the TCB is changing.
Correct.
Okay, thanks.
So in that case, between PIID and the PPID, what's the difference between those two? Is PIID more recommended, more stable? Because I think it sounds like PIID also changes with TCB updates without TD preserving, which I think is the same behavior as PPID.
Yeah, PIID and PPID have the same lifetime, so they survive the same changes that were cleared on the same changes. The difference is that PPID is very specific to PCK certificates, where PIID is a more general name for a platform identifier. So if we ever move away from sort of SGX-based attestation, we still can maintain PIIDs, but PPIDs are very specific to the PCK certificate chain.
Yeah. So our recommendation is to use PIID, right? Because of the reasons just mentioned by Jim.
Got you. So in terms of stability, they are pretty similar at this point. But you recommend PIID because even without SGX, PIID still works, but not PPID. Okay,
yes.
Thanks.
Yep, they have exactly the same lifetime. So the same things that would change PIID would change PPID.
Yep, and that's also why some of our customers like when I first talked to a customer, right? They were like, yeah, we know we have a similar idea and we use PPID. It's like, yeah, you can technically you can, but we recommend PIID. Yeah, good. I don't see any more questions, so let's continue. It doesn't get much more complex, right? But we have these problems in the strawman construction, right? So let's look into Intel's actual proposal that we also put online, and we call it here the short-term solution. It all starts again during initial supply chain or later maintenance phase. The IDs are collected for every target. The IDs are now not sent to public repository, but instead to what we call a platform endorser, which stores it in a database. And based on these IDs, the platform endorser creates POE structures. These structures are signed with a private key belonging to the platform owner. And we propose to use a standardized IETF quorum format for these structures, right? And I guess we didn't publish yet any information of what in detail it will contain, right? But at least the ID, potentially things like expirations, right? To also defend about some attacks, right? Where you forget to do an SGX factory reset or whatever. So there will be these structures signed by the platform endorser. And we then in the production phase, again, have our target platform, we have our attestation service. And somehow the attestation service now needs to get hold of this POE structures and the public key of the platform endorser. We don't tell you how to do it, right? One option is that the platform endorser sends this list to the attestation service. This doesn't solve the problem of leaking the information, right? But this might be okay if it's one party, right? If it's hypervisor A, have the platform endorser and this hypervisor has also the attestation service, yeah, okay, then why not just send it over? If it's an independent attestation service, ideally, the platform endorser would again put up some endpoint which can then be on demand requested. Like, hey, I want the POE structure for platform instance 5 or whatever, right? That's the other option. It's an implementation detail. As usual, the attestation happens, the quote is generated over. Regular quote verification happens, quote appraisal can happen, and then POE verification happens, right? But this time the process is like a little bit more complex, right? Because what has to be done? The attestation service looks at the quote, reads out the platform ID again from the PCK certificate, then gets the corresponding POE structure either from its own database or by requesting it from the endpoint. It compares the ID in the quote with the ID of the structure, checks the signature of the POE structure, especially it checks, does it match to the public key of the platform endorser? And that's it, right? As before, the attestation service made sure that the quote was created by the platform owner, by the expected platform owner, right? But this time, it doesn't have to go to a website or whatever. It looks at really a structure, a well-behaved, standardized structure, validates it versus a PK, public key. Note that Intel does not play a role in this POE-related pieces of the flow, right? We don't sign POEs. We don't create public and private keys for these POE structures. That's all the job of the platform endorser, which is basically a, let's say, role in the platform owner's infrastructure. Good. I don't see any questions, so moving on. Longer term, Intel, we want to integrate this POE structure into our existing Intel DCAP stack, right? Like not every customer, but a lot of customers use our Intel DCAP stack for generation of quotes, for verification of quotes, for handling of the collateral. So it would be cool to have all of that integrated. Yes, please, Greg. Then let's handle your question first, and Gary.
Yeah, thanks for taking my question. You probably get to this, but I'll ask it just in case you're not. Is Intel, are you thinking about what you proposed in the last slide as something that, all that's not TDX specific? Like, are you suggesting
Yes.
structures and flows that, okay, so for any TE vendor, and is there any thoughts around, is it just like standardizing the quorum format and standardizing like the logical network profiles? Like, how far do you see this going in terms of perhaps standard libraries, open source implementations of different components? And I guess one final thing is, how might this relate to CoServe, which also seems related to like the bottom arrow there, where endorsements are flowing between two systems?
Mm-hmm. Let's say the first half of it, I mentioned it at the beginning, ideally this should be vendor agnostic, right? It's, in our case, sure, there's this ID in our PCK storage, but to the best of my knowledge, AMD's collateral has something very similar, and they could do something very similar. And ideally, they will do something very similar, right? At least that's my opinion. The quorum forwards, like our code will be public, open source. Our standards, like our definition, will be open source and standard, right? So Ideally, yes, everybody uses exactly the same format. Yeah, but there's only so much we can do, right? We can't force infrastructure providers to do it. I guess we need an ecosystem, right, to do it. And also, we can obviously not force AMD or ARM to do something similar or in a similar way. But I think it would be good for the community if we would do.
I'm sorry, just one. Have there been any discussions with anybody from AMD? I know in Azure here where I work, we're internal to Azure. We're working on basically something very similar to this for some of our SMP based systems, and there's a larger effort going on. It'd be good to rationalize what we're doing here with what you're doing, and potentially if AMD wants to weigh in with some opinions. So
Yeah,
is there a broader, yeah.
do you want me to do it? Do you want me to answer that, or do you want Benny to answer it? Because I think it's kind of putting Benny on
Gary,
the
please.
spot.
No, please.
Yeah,
Go
whoever
ahead.
if there's wherever if there's any broader discussions happening, I'd love to know about them and then plug in as possible.
Yeah. I think you can you can get in touch with the gentleman named John Lang in your organization to get you up to speed on what's being
Hmm.
discussed with respect to S&P, and he can probably tie in the comparison with TDX and S&P. I tried to post something in the chat window on the on how OCP has defined something called PKI. I'll call it PKI transfer, which I don't. I'm not looking at the way Calyptra has implemented it in front of me, but Calyptra has a way of generating CSRs where what I'll call an owner or even a tenant can actually bootstrapping from a hardware-based attestation can actually replace with their own PKI. Now, in that kind of approach, the PKI can actually, the owner PKI can actually serve as an endorsement of the platform. So, and that can actually, I believe it can actually be persisted in the Calyptra subsystem itself. So that's one approach, and that's one approach. And AMD was very heavily involved with not only defining the OCP specification, but also defining the Calyptra mechanisms to actually support that. So you're still not getting perfect alignment there between um, a Calyptra-based platform and TDX, though. So I think so I don't think it quite solves the issue that you're looking for, Greg. Yeah, because I think
Well,
you want perfect alignment on the cert chains, right?
Well, I mean, quite frankly, we're doing something internal, or we're
Mhm.
working on something internal that looks almost, at logical level and nosebleed level looks identical to this. There's CORIM based
Mhm.
endorsements essentially communicating the same sort of information at the
Mhm.
moment about, Civ SMP hardware and it's, as Benny said, all this stuff he said, Intel has nothing to do with this, right? Anybody, and you even had somebody doing PPID based versions of this. So it's kind of, folks can, invent the wheel, but we shouldn't all the spirit of my stuff is we shouldn't all reinvent the wheel and standardize as much as possible and share, you know, designs and code as much as possible.
Let me say something here, and Benny can certainly disabuse me of my notion, but I mean the OCP slash Calyptra based approach allows for keeps the SOC vendor out of the loop on the verification process. So basically, what ends up happening is that once the hardware attestation is verified by the owner replaces with their own PKI, and that's it. Now, as far as I can tell here in this diagram, thank you for this diagram. Thank you for this presentation, by the way, Benny. It's very informative. The the Intel, as far as I can tell, is in the loop. Now, it doesn't mean that it's constantly in the loop for every single attestation verification, but there is a point in time where the POEs have to be retrieved, right? And
But maybe directly to that, no, Intel is
yeah.
not at all in the loop.
Well, okay, but
During registration, only during registration,
Mhm.
like one-time setup, but that's
Yeah,
it.
Yeah. So, so that would be the kind of if there is a difference, that seems like from an operational perspective, that would be the difference. If you have a collector-based system, the
But I guess
SOC
that's the general.
infrastructure is never it doesn't have to be in the loop. Yeah.
But I guess that's just a general difference between Intel TDX and AMD SEV SMP, right? That's just the difference. Like we need this registration step, you don't. That's it, right?
Mhm.
In this attestation flow at the beginning, right? But for PoE, like Intel is at no point, like PoE does not add any additional interaction with Intel. That's important.
Okay.
On AMD, you don't have to register, but you still have to download the certificates, right? So there's a point of contact.
For non-collector-based systems, that is absolutely right. They call it like key distribution service. Um,
Yeah.
for yeah, as I said, for collector-based systems, there should be no reason for that unless you're talking about, for instance, the trust anchors. That I guess you have to interact with the SoC vendor if it's required. Yeah.
For us, we require the customer to go and get those. Well, we can do it automatically for them, or they can go and get the trust anchors and bring them in.
Yeah.
So in both cases, there's a reach out to either Intel services or AMD services. In general, we generalize the term as registration, even though it's not really registration in the case of AMD.
Yeah.
But to keep it sane for the customer, we put it under the same umbrella.
Yeah.
Okay, but I guess I would propose let's go on. Right, you only have 5
go
more
ahead.
minutes and just like a little bit of stuff to cover. So as I said, like this was just a short-term thing, right? To get it going out as fast as possible. Again, with the goal of not everybody reinventing the wheel. But longer term, at the moment, Intel DCAP is our attestation stack, right, for generation and verification. So our first target is to integrate it there. The first step is again collect the IDs. No surprise. Get the IDs, create and sign these things. But what is different now? The POEs are returned back to the target platform. Exactly. So where the target platform then keeps these POE structures is again implementation specific. We don't tell you how to do that, but it might, for example, sit on a specific location in the host OS that whenever a code is generated, just get it from that location and use it. Because that's what we see during productation phase, or this communication now, right, between the endorser and the attestation service is even reduced now because it only requires somehow to transfer the public key. Like it can be website of the platform owner or an endpoint again. Like only thing needed is this public key. Attestation happens again, but this time, like the quote is generated again, but this time this POE structure is just attached to the quote. Right? At the moment, we have already the quote and we have the certificate chain. Just if you would put the POE at the bottom of it, this would even like reduce the entire flow. Code verification happens, POE verification happens exactly as before, right? So the main difference of this flow here is POE will just be on the target platform, and during quote generation, it will be attached to the quote. Yeah. Pretty easy. Thomas, please.
Sorry, I might be missing something, but how revocation of that information happens if the only thing that the platform endorser shares with the attestation service is the public key for verifying the thing,
Yeah.
then they are basically infinite.
I understand your question, right? And I don't even know if we have specified it. We should. I think I should talk with Jim about it.
The question about the POE format itself?
No, how would the platform owner revoke a POE structure? And I think it's a good question that we don't have to find.
It's a good question. I think it's going to have a certificate chain. I think you would do the same way that you revoke X509.
Yeah, but it has to be an endpoint of the owner now, right? That has to be a revocation list or something, right? So it is a bit.
Yep. Is there, to me, that just sounds like a general question of how do you revoke a CORIM endorsement, which could be, which may be the X509 based or may be based on the validity interval inside of there and the time range for that and reissuance but it sounds sounds like a general CORIM revocation question.
Yeah.
I don't know
Yeah,
what's
exactly.
specific here.
Platform owner somehow has to revoke it. I said we didn't define it yet. I guess we will discuss it internally. Hank, please.
Yeah, hi, this is Hank. So some people might say that revocation should only happen when you are messing with your key management, like the key got lost or stolen or somehow compromised, and not when the information that's in that that's side with that key is outdated.
Yeah,
or not applicable or dangerous to apply now. So maybe revocation is not a tool for all here. It certainly works, but semantically revocation is for key mismanagement, right?
Yeah, I think a validity range would be one other way, right? So that these are reissued.
Yeah. Yeah, and as mentioned, right, they should have at least an expiration date, ideally, right? And then it will at least solve at some point. Sure, it's not ideal and it has to be revoked, but I guess we will have to look into this again. Just a few minutes left. I just want to say, sure, at Intel, we would want to make, as said, we want to make it easy for customers, but we also want to share it with the world, open source. So we deliver tools to make the crucial parts of that flow. We already have since a few weeks now, and what we call an Intel PoE generator, which is here step one, to collect these IDs from different of our structures. We have this public now. This generation tool is not public yet, but should become public soon. And then for verification, it's a bit more complex. Yes, there will be a standalone tool be available also soon, but in a phase 3, but not in DCAP. It will first be standalone, and then later it will be integrated in DCAP in what we call phase 3. Note these colors here match what I presented in the flow before. So when you look back at the slides, you will see which tool can be used at what point. There is a much more complex flow, or not that much more complex, and I guess we only have 1 more minute, so I guess I assume you end early, so we will not talk through it in detail. But I just want to open it up for you. If you ever have a question about it, come back to me. I just want to talk about the main goal. Like the main goal of this more complex flow here is to make sure that the platform is composed exclusively of CPUs that are owned by the endorser, and especially only a not fully trusted maintenance administrator. So an administrator in that phase should not be able to create valid PoE structures. Only really hand-selected subset of administrators that are fully trusted to the extent what is possible. They collect what we call device IDs, like an ID that is embedded in every CPU that never changes. These highly trusted administrators will read this device ID out. The device ID will be collected here. I will jump over all of this, but now it involves Intel. That's important. The platform manifest is sent to Intel. Intel sends back, yes, this is now a composition of, we call platform composition manifest. So these are really Intel owned, like original Intel CPUs that are now together on the platform. And it's basically by doing this trickery here, so to say, we make sure that your everyday maintenance administrator, they will not be able to generate PoE structures for a system that is not owned by the platform owner that you want. And only this was my last slide. For this more complicated flow, we also will bring the tools out. They are only in phase 3. I mentioned it here without any timelines, right? But just that you see a relative perspective. We will concentrate on the other tools first and deliver this tool later. And with that, there is the PoE specification is public, as said, since last November, December. So it's out since a while, and we will try to keep it up to date. And that is it. Thank you very much.
Thanks, Benny. Thanks for the excellent presentation. One question: can you share the slides so that we can upload them to the?
Absolutely, yes.
Thanks very much. And secondly, maybe I missed it, but is there any plan to publish the quorum endorsement format anytime soon?
Yes.
Okay. Thanks. Thanks, Benny. Okay, we need to wrap up now. Sorry, it's 2 past. But again, fantastic presentation. Thanks very much.
Thank you very much, guys.
See you in a couple of weeks. Bye-bye. Cheers.